So it's time for part 3 of lecture 8. This is the discussion of the wave equation that follows from Maxwell's equations, and this will include the demonstration that the speed of light is the speed limit of special relativity. Right? At this point we've had the speed limit and it appears in the Lorentz transformation. We haven't had to identify it with the speed of light. Well, we've done it informally, just to do phenomenology lots of times. But now we can forget all of that and just make the point that the speed limit that appears in the Lorentz transformation, okay, becomes the speed of light when we develop the wave equation for electromagnetism. Okay, so let's remember a few things about waves. Some of this is just a review for you, nothing special about light. Just understand how to parameterize a wave, and then let's imagine a wave solution to Maxwell's equations, and see what that implies, and then let's get the wave equation for light. So at this point, the electromagnetic field is becoming a dynamical object, okay, and it's going to be able to propagate on its own, free of sources. So very different from Newton's world, where you have an electric charge which carries around an electric field with it. That electric field is Galilean invariant, and that's the whole story. In this case, of course, we can create spherical waves, outgoing spherical waves, electromagnetic waves, by accelerating a charge. Okay, spherical waves will develop and propagate it out at the speed of light. So in the first part of the discussion, we're not going to look at the sources for the wave. We want to establish that the wave is an independent degree of freedom. So we'll be looking at space-time points where there's no charge or current density. Then at the end, let's just briefly sketch what happens in the vicinity of charges. Now the textbook does a lot more than this, okay, and there are several appendices and such which develop the wave equation, okay, and solve it, discuss retarded propagators, retarded potentials, okay, potentials that take into account the finite speed of light, and we'll be discussing those aspects of the textbook in the recitation section, but that's a little bit too detailed for these general lectures, but one should be aware of that and take advantage of that material in the textbook. There's a lot more in the textbook on electromagnetism than we're covering in these overall lectures. Okay, to begin, how do we describe a traveling wave? So I imagine a wave that's moving in the direction of a k vector at a velocity v. And I remember that I represent that wave by a function a, some waveform, okay? Imagine a wave on the ocean having a shape of a breaker, for example. And then it's a function of the inner product of k with r minus vt, okay? So for example, let's say the wave is moving in the x direction, so k only has a component in the x direction. And then the argument of the wave becomes just k sub x, parenthesis x minus velocity in the x direction time. Okay, so I have this wave moving along, and I might look at one point on that wave. Okay, again, it might be a water wave that's just a solitary wave moving across a basin, something like that. So I specify a value for x. So I have to therefore have the argument of the waveform be constant. I specify a value for the waveform, the height of the wave, say, and so I'm looking at a point where the argument is a constant. And where is the argument a constant? Well, I see the argument goes like x minus v sub xt. So I see that that point on the waveform is moving in the x direction with a velocity v sub x. Just set this parenthesis to a constant, and you get x is equal to vt plus a constant. It's moving to the right at a velocity of v sub x in this particular case, where where the waveform is pointing in the k direction, which is the x direction. Okay, so you see I can write that for the argument this way, and I can identify what each of those terms mean. So in the textbook you'll write this sort of thing down. You might specialize to a periodic motion, okay, in which case this vector k becomes essentially 2 pi over the wavelength in magnitude, okay, and you'll study that. Then also you'll try to write the amplitude in an invariant form. Okay, so it's a wavelength. It's a wave of light. It travels at the speed of light, as we'll show. Okay, and so its state is Lorentz invariant. Same in every frame. Okay, and so you can write the argument as a frame-independent phase, the dot product of two 4 vectors, and you'll do that in the text and in the problems. Okay, so you'll play with this a little bit more, but I think we all know how to parameterize a moving waveform, and that's all I need for the moment. So therefore, I'm looking for solutions of the Maxwell equations of that form, where the electric field, its argument is that which describes a wave, and similarly for the magnetic field. We'll look for solutions of this kind, and find them. And like I said, I'm going to look for the solutions in free space. Okay, so I want to divest myself of the charge and the current density, because I want to see that the electromagnetic field can propagate as an independent dynamical degree of freedom. So here, then I've written down in some region of space where there's no sources. Okay, Maxwell's equations. Okay. Now, just to clean up the notation, let's call the phase, just give it a name, call it alpha. Okay, and let's put these forms into Maxwell's equations and see what it says about the electric field and the magnetic field of a traveling wave. The first thing I do that for the electric field. I put it into Gauss's law with no source, and then I have to take the divergence of it. Well, the easiest way to do that is use the chain rule. The electric field argument is only one variable, just the phase, but the phase depends on x, y, and z. So that's what I've done here. Okay, so I've written the divergence as the derivative of E with respect to alpha, and then I've taken alpha derivative with respect to x, y, or z. Well, look at the phase. If I derive the phase with respect to x, y, or z, that picks out k, and that's what I've written down here. Okay, so that's all there is to it. It's a dot product here because it's a dot product here. Then I can pull out the d by d alpha and have the k dot e is equal to 0. Okay, the E field is non-trivial. The alpha dependence is what it is. So the only way I'm going to get this to be 0 is in fact that k dot e be equal to 0. Okay. Okay. So what does that mean? Well, I have a wave that's traveling in the x direction, and I see that k dot e is equal to 0. So the electric field is perpendicular to the direction of propagation. Okay. Well, let's choose the direction of the E field and call that the y-axis. Just rotate your axes, y-z axis, around the x direction until the E field coincides with the y direction. Let's call that the y direction, just to clean up the notation. I want the notation to be as simple as possible, as usual. Okay, so k is going in the x direction, and E points in the y direction. Okay, great, that's simple. Now let's look at the second Maxwell's equation. It says that the B field is divergence free. So I put into it the B field traveling wave, okay, and I learn again that the B field is perpendicular to the direction of propagation. Okay, now I'd like to relate the E field to the B field, and I can pick one of the other Maxwell's equations. To do that, I chose to write down Faraday's law, okay, and then I have to take the curl of E, but remember, E, it points in the y direction, and so the curl of E, the only bits that remain, is that it points in the z direction, okay, and its argument is the E sub y dx, just taking curl. Okay, So therefore, putting that back in here, I see that that's equal to the time derivative of the B field. I learned that the B field points in the Z direction. The B field has to be perpendicular to K, and Z is perpendicular to K because K is in the X direction. So here's the picture then of the traveling wave. In this case, I have it moving toward me, and I have E in the Y direction and Z down. Okay, so right-handed coordinate system, so E cross B is in the direction K. Okay, that's what I infer from this. Okay, I mean I did it for special X, Y's, and Z's, but the geometric idea is the configuration of the three vectors, you see, and how you characterize that in general, free of coordinates, is that E cross B is in the direction K. Okay, and that's what's stated here. Well, in the textbook, you'll discuss momentum, the momentum carried by the wave, the energy carried by the wave. Okay, and you'll see that E cross B is the flux of the energy of the wave, and so that makes sense. Okay, the wave carries energy, and it's made out of E cross B, which points in the direction of propagation. Okay, I don't need all that here. I just need to get the properties of E and B. Okay, but now we're all set. Now we're all set. Now I can take the fact that the electric field points in the Y direction, the B field points in the Z direction, and put that into the Ampere's law and Faraday's law, and that's what I've done here. So it's cleaned up a lot because I've chosen the coordinates in a simple way so we can see how the algebra works. There are a couple equations. Okay, gradients of B sub Z feed into EY, and gradients of EY feed into BZ. So I want to diagonalize this, set these two first order equations, and to do that I take appropriate derivatives, make it into a second order differential equation, and isolate E sub Y in one and B sub Z in the other. So what do I do here? So I'll take d by dt on the first one here, see? Okay, and I'll take minus d by dx on the second one there, and then I get these two equations. Okay, I see that in that case the mixed derivative of dt dx occurs in both of them. This is why I chose to do those operations, and so I see I can eliminate between the two equations E sub y and an equation just for b. Okay, so I do that, and I see that b sub z satisfies this equation. Second derivative with respect to x minus second derivative with respect to t divided by the speed limit squared applied to b is equal to 0, and similarly for E sub y. Okay. Okay. So now finally I can substitute into one of these equations the traveling wave form, and I do that here for b sub z, and I take my derivatives. Okay, well that's particularly easy. Again, I'll do those derivatives by using the chain rule, because the argument of the traveling wave is particularly simple. It's just a phase. Okay, and the phase depends upon x, y, and z. And so just doing those operations, I'll get on the right hand side k squared, and then in parentheses 1 minus v squared over c squared. Okay, and how does that happen? Let's check on that second term. That's critical. I take d by dt twice on this thing, right? And I see that the prefactor of t is v. So I'm going to get two factors of v upstairs, and I get two factors of the speed limit downstairs. And so I get this parenthesis in the right-hand side of the equation. It's simple, but that's critical. Okay, because remember, this equation is this wave operator applied to b equals 0. So this algebraic expression has to be equal to 0 in all cases. Well, how could it possibly be equal to 0? Well, it has to be, k is not 0, alpha dependence of b is not 0. It has to be that 1 minus v squared over c squared is equal to 0. In other words, v must be c, and that's the point. Okay, so we learn that the electromagnetic field satisfies a wave equation, okay, with the speed limit in it, and then when we look for solutions of it, we learn that speed limit is the speed of propagation of the wave, and that was the point that we wanted to make. Okay, that's been promised for a long time, and it's nice to finally settle on it. Okay, now of course I can do a little bit more algebra. I won't do it here. It's done in the textbook, and write down the wave equation in this whole discussion in a general fashion. Okay, for general waves propagating in space-time, and then in particular, okay, my wave equation in one dimension will become a wave equation in 3 dimensions, and my second derivative with respect to x will be second derivative with respect to x plus similar term in the y direction and a similar term in the z direction. Okay, so you'll do that sort of thing in the problems. That's just generalized to a B in an E field, just generalized to the case that K points in any old direction, and then it's easy to do this. So I did the simplest special case, and it's just more of the same to do that, to get the general case. Okay, and so I see wave equation in 3 dimensions, and similarly I get the transversality conditions, that the electric field and the magnetic field are perpendicular to the direction of propagation. Then I look at Faraday's and Ampere's law and find that the electric field, in the case of linearly polarized fields, which I'm looking for here, that in that case that the E will point in one direction, the B field will be perpendicular to it, but also transverse to K, and E cross B will be in the direction K. Okay, now this combination of space and time derivatives, we've seen it before. It's very important. It's the wave equation. It's an invariant operator. Okay, I write it. Well, it's written in every which way in various textbooks, and I'm probably not consistent with it either. So it's written as box squared as the second time derivative minus gradient squared. I slipped in a minus sign here, so it's, I guess I have one conventional definition of it. You see, and at this point it's always been wave equation equals a field equals 0, so authors like to choose whatever the sign comes up there. And I think for us it's nicest to write d by dt squared first, and so I'll do that here. Okay, it's an invariant operator, and it states that waves travel at the speed limit c in all frames. Right? It's invariant. So if I get the wave equation for the electric or the magnetic field, then it's box squared on E is equal to 0, box squared on B is equal to 0. Then I go to another frame and I do the same thing, okay, and I'll still have box squared, okay, and it'll involve the same C. Okay, we saw that c was the velocity of the wave. I can make that argument in 2 frames, and use the variance of the wave operator, and I see that this states that the speed of light is the same in all frames. Okay, it's a universal constant, and so now we proved that point, and that point, of course, is so essential in relativity. Okay, so well, we've done this sort of thing before, and I just want to emphasize it here, you know, that I can close the loop, do that argument again, okay, knowing full well the important point, okay, that the wave operator is invariant, is a Lorentz invariant. Okay, so the next subtopic we want to look at is what happens in the case that we have sources. I'm not going to do much of the algebra here. I'm just going to be descriptive, just to give you the ideas. Again, there's a lot more algebra in all of this than I want to do in these lectures. So we do it in recitation or in the books, and the book has it does it in detail. And it solves, for example, it sets up the general solution for the electric and the magnetic fields, okay, outside an arbitrary source. So it discusses retarded time and retarded propagators, stuff like that. Okay, So how is radiation created? Well, we all know that you create a wave by accelerating a charge. Okay, if you have a charge that's moving at a constant velocity, and it carries its fields with it, so to speak. We did that case. Remember, we looked at the electric field in that particular situation. We could have done the magnetic field as well, but we did it in the second part of that lecture, and saw that the B field was proportional to 1 over c squared V cross E. Okay, and E travels with the charge. It's pancake form due to Lorentz contractions, and that's fine. But now if you want to create an electromagnetic field which is free of the source, you just have to put some work into it by accelerating the charge. Okay, we all know that from radio waves. How do you make radio waves? Okay, for point sources, the radiation will become spherical waves whose amplitudes fall off as 1 over r. Right? The electric field, okay, between stationary charges in a particular frame, of course, falls off as 1 over r squared, as we've seen from Coulomb's law and deduced from Gauss's law. Okay, but now if we make free radiation by having an antenna, then that electric field and that magnetic field that's propagating away falls off at a much lower rate, 1 upon r. Okay, now the energy carried by that wave is quadratic in E and B, and the energy carried by the wave falls off as 1 over r squared. Okay, so then if you calculate the total energy flux that propagates to infinity through a very large sphere, you see that the energy density that's carried by the wave falls off as 1 upon r squared, but the surface area of the sphere grows like r squared. You'll find that a finite amount of energy propagates to infinity. Okay, and that's the character of radiation of light, and of course that's the idea of seeing a star in the sky. You can see it because it carries energy off to infinity. Okay, which influences our retina. Okay, and that's what's stated here. So I'm just emphasizing here the special features of radiated fields from a point source. You start with a point source, do that one, and then make complicated sources out of a bunch of points, and you'll use linear superposition to handle the more complicated cases. Okay, but at this point, okay, we've written down Maxwell's equations, and they have not involved accelerating charges, right? We can calculate E cross B at the points of the sources just in terms of the charge density and the current density at that point. Okay, and we trace that simplicity back to the fact that of Gauss's law, which makes this statement that charges and only charges are the sources of electric fields. Okay, so we're firm on that. Okay, so how can it be? Where in the formalism does it come that accelerating charges make traveling waves? Okay, well, the point is, when we went to the wave equation, remember, that was a second order differential equation. So there's another set of derivatives that you have to take to make the equation for the traveling wave, the wave operator, second order. And in that process, you're going to differentiate the sources and go from quantities that depend on velocities to quantities that depend on accelerations. Okay, so that's done. That's sketched here. I go back to my full Maxwell's equations with sources to get the wave equation with sources, and I do similar arithmetic, well, algebra, juggling the derivatives d by dt and gradients and divergences and curls to write the general cases. So it's just do the algebra like we did in the sourceless case, but keep track of the right-hand side. The right-hand side being 0 in the sourceless case, and in this case now being j and rho. Okay, so I do that and check the textbook for the details. Again, it's an exercise in vector calculus, Q1, And you'll get that the wave operator on the E field is equal to two terms, one involving the spatial gradient of rho, and the second one being the time derivative of the current density. And you'll get that the wave equation for the magnetic field has a source which goes like the curl of the current density. Okay. Okay. And so here you see it. So now we're sensitive to the gradients in both space and time of the source. And this term in particular is the one we usually think about when we're thinking about radiation. The time derivative of J is what's matter. It's the acceleration of the charges that matters in simple application of this formula. Okay. Now in the textbook you'll derive these formulas in several different ways. One of the ways you'll do it is to introduce electromagnetic potentials. So in addition to the E and B field, you'll develop a way of calculating those E's and B fields from a 4 vector called A upper mu, and there'll be a formula for doing it. Okay, and then you'll do something called choosing a gauge for A upper mu, and you'll choose a Lorentz gauge, and you'll find that the potential, the electromagnetic potential, satisfies a wave equation in the presence of sources, which is as simple as possible, just that box squared applied to A is equal to J. No derivatives of J at this point. Okay, it's a simple equation. But then to get the wave equations for E and B, you have to do derivatives on the potential, and that's where these extra derivatives come in. So check out the textbook for all of that. But I think we have the idea here. I'm just emphasizing the concept that although the Maxwell's equations are first order and just sense the quality of the source through its 4 vector current density, that the wave equation, being a second order equation, is sensitive to the derivatives of the sources. Okay, so now let's also remember what happens when a point charge radiates. I just want to say some of the words here again and write down a formula that I'm stealing from Landau and Lifshitz that shows that the radiated fields fall off like 1 upon R. So here's a complicated little drawing. I have the x, y, and z axis in the lab, and I have a particle with charge q that's making some trajectory like that. It has a velocity v and a charge q, and I put it into a curved trajectory, so you see it's accelerating. And then I want to know what the electric field is at this point R. Okay. And so I solve my wave equation in that particular case. And then one of the important variables that comes out of that solution is the fact that to determine the electric field at this point R and T, I have to know, okay, the state of the source at an earlier time, called a retarded time. And the retarded time accounts for the fact that the wave travels at the speed of light. Okay, so to determine E over here at R and T, I have to know the state of the charge at an earlier time, and the time is determined by the expression that the distance between the source and the sink is equal to c times the time difference. So T sub R is a retarded time, and so R is the distance that the light travels if it's emitted here at time T sub R and is observed here at the time T. Okay, so R sub P of T is of T of R is the position of the charge when it radiates fields that are going to be observed at R at the time T. So so you have to include, of course, the fact that information can travel at most at the speed of light. In this case, at the speed of light, and that makes the solution and the description a little bit more intricate. Okay, and you talk about the retarded time and retarded potentials because of that. Okay, and then I've written down the formula here for this variable R between the source point and the sink. Well, you see, it's an implicit equation now for the retarded time, and so when you take derivatives with respect to time, in this context, you have to be very clever and careful. Okay, well, Landau's careful and clever, so he goes through the calculation. I encourage you to look at bits of that as in your easier textbook than Landau and Lifshitz. Okay, and we find that the electric field at the point R and T consists of two terms. Okay, okay. One of the terms here that's proportional to the velocity of the charge. Okay, U. It falls off as in R as, let's see, R over R cubed. That's 1 over R squared. So this is the first term is the electric field that's carried by the source. That's not of interest here. And then there's a second term. Oh, it's rather intricate. Its direction is this R between the source and the sink. Okay. At the time, the retarded time. Okay. And it goes like R cross U cross A, where A is the acceleration at the retarded time. Okay, and that's what I'm interested in, because now look at it. It has two R's upstairs, right? R is the distance between the source and the sink. That's written down here, so that's the R that's relevant. It has two R's upstairs and three R's downstairs. So it falls off like 1 over R. That's what we're looking for. That's the spherical wave that's generated by the acceleration of the charge. And here this term is proportional to A. If I put the argument in there, that's A at the retarded time, of course. And that's the details, more details are written down here. And that's what I wanted to emphasize here. So the second term goes like the acceleration at TR. This outgoing spherical wave, it falls off like 1 upon R. And the first term, okay, the first term, the fields that carried with the charge fall off like 1 over R squared. And the second term, the radiated wave, falls off like 1 upon R, and that's what we would be looking for. Okay, so the equations are generally a little bit complicated. Time-dependent problems in electrodynamics is quite complicated. That's why the textbook by Jackson, okay, it's so many hundred pages long. Okay, and Landau and Lifshitz do some of this, and there's a bit of a sketch of it in the textbook that we're doing here, the relativity, electrodynamics, and general relativity textbook. But we don't get into it in great detail, because, as you see, it is intricate. Okay, what we're more interested is the foundations that lie beneath it, and that's what we've emphasized in this lecture.